Go ahead and make it louder.
Okay,
If
on
you can't hear
behalf
that.
of the MIT Club of Rhode Island, welcome to our first Zoom event in 2022. We're really happy that you could join us this evening. Before, again, introducing our speaker, though, just a few household items. Please mute your laptops or phone if you're calling in. And then at the end, Dr. Brushett will take some questions. So he'll be presenting his talk. So without further ado, I want to introduce him because he's got a number of slides there. And so we really look forward to his presentation. So Dr. Brushett, welcome. He's the associate professor in the Department of Chemical Engineering at MIT, where he holds the Cecil and Ida Green Career Development Chair. Before joining the Institute, he received his PhD in chemical engineering from the University of Illinois at Urbana-Champaign and performed postdoctoral work in the Electrochemical Energy Storage Group at Argonne National Laboratory. His research group seeks to advance the science and engineering of electrochemical.
Okay, I got it. Well,
I'm gonna hang up.
all right, bye-bye.
Yeah, sorry.
The person whose name is Daniel, can you go on mute?
Yes, please.
Daniel, can you hear us? Your Zoom ID is Daniel. Who's the master? Because you can mute him. Whoever is the host can
Yeah,
mute.
1
Daniel.
minute. Yeah, I will mute him. There
Yeah.
we go. All right, sorry for the interruption. Dr. Brushett is interested in the fundamental processes that define the performance, cost, and lifetime of present day and future electrochemical systems. His group currently works on rechargeable batteries for grid energy storage and electrochemical processes for carbon management. He also serves as the research integration co-lead for the Joint Center for Energy Storage Research, a DOE-funded energy innovation hub. So without further ado, please welcome Dr. Brushett.
Thank you so much for the kind introduction. Juan, thank you for the invitation. Paul and other members of this club. I wish I could be with you, but as we were talking about, I think we'll be remote for at least the next few months or so, but hopefully I'll get an opportunity to visit you guys. Rhode Island is not too far away. In fact, my wife works in East Providence, so I know she can drive down there and back. So this evening, I have a few slides prepared, about 30 or so. And what I'm going to try to do is give you a sense as to the role that grid scale energy storage can play in meeting our goals for sustainability and a low carbon energy economy in a cost effective fashion. I'll particularly talk about flow batteries, but I want to start off by saying that I suspect we will need a number of different energy storage and energy conversion devices to enable this transition. Flow batteries are one of these technologies, but it should not preclude other applications. And then hopefully I'll leave some time for some Q&A at the end, but I'm happy to go past 8 o'clock to get all the questions that we need. And then I'm the only Fikile Brushett that I know, so I should be pretty easy to find online. So let me see here. Let me just go ahead and start the share. So we did this beforehand. So maybe Juan, you could give me a thumbs up to say that you can see the slides.
We're good.
All right, brilliant. Thank you so much. Okay, let me just do one more thing here. Get my laser pointer ready. Excellent. So again, thank you for the invitation. And I wanted to start off perhaps in a place where maybe everybody on this call is quite familiar, which is the increasing energy consumption worldwide that's projected for the first part of this century and actually continuing to move forward. The availability, abundance, and energy density of fossil fuel resources has really driven progress over the last century. And this has led to dramatic improvements in quality of life worldwide. So you can think of things like the emergence of a burgeoning middle class, increasing urbanization, and the rapid growth in emerging economies such as India and China. But despite the ample supply of these inexpensive fossil resources, there is a growing global consensus on the importance of climate change and increasingly urgent need to reduce carbon emissions without stifling economic growth. And so while this increase in energy demand itself is not necessarily a poor thing, the challenge is how closely carbon emissions are tied to this energy consumption and the impacts of climate change. And so this is a very important problem because the scope, scale of this challenge is particularly daunting because it involves significant changes in electricity generation, in transportation, and in industrial processes, which are vastly larger than almost any other human activity. While energy consumption is seen to be increasing dramatically worldwide, in OECD countries, which are the Organization for Economic Cooperation and Development, so you can think of these as essentially the developed world, the energy consumption is not seen to grow that fast, that quickly, but this kind of masks a little bit. These are yearly averages. It masks changes in the peaks. And maybe this can be seen if we look at the next slide here, looking at the stresses on grid infrastructure within the United States itself. And I'm just giving you two recent examples. One in August 2020 in California had to issue rolling blackouts due to extremely hot summers and the demand for residential and industrial cooling stressed electricity demands and necessitated statewide rolling blackouts for the first time in a couple of decades. And then last winter, the Texas grid nearly failed due to extremely cold weather, leaving many without power in some of the coldest times of the year. And so in many cases, there's a need for, even within more developed countries, a more resilient and sustainable energy system. However, we're making progress. Over the past 10 years or so, the cost of solar and wind has plummeted. I'm giving you an example of solar here. This is from Lawrence Berkeley National Laboratory, and it looks as the cost of solar starting in about 2008 and going until about 2018, where the costs have dropped from on the order of about 20 to 25 cents per kilowatt hour to something lower like 5 to 6 cents per kilowatt hour, and even as low as 1 to 2 cents in certain regions of the world. And so if we look at these power of purchase agreements, which is this PPA, you can really see that there's been significant amounts of cost reductions for different solar installations. And what you've also noticed is that we've gone from installing solar in California in the Southwest, areas that are sun drenched, and actually start to see solar installations pop up in Hawaii, the Midwest, the Northwest, and even the Northeast up here, where of course it's a little bit more expensive, but the fact is we're beginning to build these kind of systems out. If we look worldwide at unsubsidized PPAs, it's subsidized within the US. In sun-drenched parts of the world like Peru, Mexico, Dubai, and Chile, you can actually see there's a significant amount of solar electricity that's being put in at a relatively low cost. In fact, if we look at this graph here on the right-hand side of the screen, or left-hand side of the screen, actually, what you can see here is that the levelized cost of electricity for something like solar is significantly, and wind are significantly lower than other forms of electricity generation. So this is all very promising, but there's a pretty important thing to note here, and that is that if we look at all of the contracts that have gone in, this is actually a relatively small amount of power that's generated as compared to the fossil generation assets worldwide. That is to say that while we are increasingly deploying renewable assets, still the majority of the generation fleet is based upon fossil fuels. And as we begin to build out more of these renewable electricity generators, we're going to start to run into problems of resource intermittency. And I think this is nicely captured on this graph right here. This is a busy graph, but I think it becomes more interesting the more you look at it. What you're looking at here on the y-axis is every month of the year, and on the x-axis is every day of that month. And so this basically shows you the hourly variability of wind and solar resource in Texas. This is from ERCOT in 2014. And they've all been normalized, so you can look at them on the same graph. And essentially what you can see is that this black line here represents the load or the demand from the from society. The red bars here represent solar, and the blue represents wind. And what we want to take away from this is that there's variability that exists within these renewable resources, right? Some of the variability is a little bit predictable. For example, the sun goes up, the sun goes down, right? But there's also variability in terms of, the strength of the sun, say, for example, in the middle of the summer in Texas versus in the winter. right? And there's also variability in sort of how much electricity can be generated from that resource in different times of the same month. All of this is to say that the shape of the resource availability does not match very well the demand of electricity. And these inherent difficulties in turning this intermittent output for say photovoltaic or wind into reliable dispatchable sources of electrical power is likely to be a very important problem and an important constraint for the large scale deployment of PV in the future. So even if we can build it cheaply, we need to also come up with cost-effective energy management technologies, right? Now I'm going to talk about energy storage as a way of beginning to manage the intermittency of these resources over multiple timescales. But there are other ways to manage this intermittency, including transmission and distribution upgrading and demand side management as well. I will not talk about that today, but I wanted to make sure that those are also seen as solutions that could be used in this area. And so what my group tries to do is ask ourselves a question of, what would it take for renewables to be the basis of a sustainable energy economy, right? And so if we wanted to make a sustainable economy relying almost entirely on solar or wind, or at least very high fractions, the first thing we need to do is think about electricity generation, baseload power generation, advanced electric grid infrastructure, and even microgrids or off-grid type storage in order to enable the use of these resources. If we're able to decarbonize electricity sufficiently, then the decarbonization of transportation will become a little bit easier. While there exist today fuel cell and battery powered vehicles, those vehicles will plug into the wall to recharge. And when you plug into the wall, you're essentially getting electrons from a thermal generation power plant up the road. And so in many cases, you're shifting emissions from the tailpipe up the road to the local power plant. And so unless you have a carbon capture infrastructure on the back end of that power plant, the carbon dioxide is still being emitted, right? And as a result, if we can decarbonize electricity generation, this may enable the decarbonization of personal vehicles. And then ultimately, we may be able to start to think about decarbonizing industries. So using electrochemical reactions or electrically driven processes in fuel and chemical production to enable process intensification, and also to enable environmental remediation. So when my group looks at this problem, we see all of these possibilities laid out in front of us, but we believe that we need to start off with decarbonization of electricity and providing reliable, cost-effective electricity from renewable resources before these next changes can be made. And so I wanted to start off with a fairly simple representation of the grid, and talk a little bit about how storage is done right now in the grid. So typically in a grid, you have fossil generation, and that fossil generation will go out through a transmission and distribution grid and eventually go to our homes and residences right now, or to industry or other sorts of use cases. And this electricity is delivered just in time. So depending upon how much electricity we need, the fossil plant can be ramped up or ramped down to meet that electricity demand. When you start to introduce renewables into the mix here, you start to get a little bit of intermittency. And these are the things that we're worried about, the ability to ramp up or ramp down with intermittent renewables in order to meet the demands of society. And so if you wanted to store electricity today, most likely you're talking about pumped hydroelectric storage. It represents the majority of energy storage worldwide. We'll come to why this is in a second, but largely speaking, it's because it's absolutely massive as compared to most other installations, right? The way pumped hydro works is you actually store water at two different elevations, right? And you're relying on the potential energy of water to store energy. And so what'll happen, just to give you an example here on this river right here, I believe this is from the Tennessee Valley Authority, is that to store electricity, you pump this water uphill, right? Using the electrical energy to drive the pump, push the water uphill. And then when you want to get electricity, you let the water from the reservoir flow back downhill. It flows through a turbine. That turbine spins up and generates electricity, and that electricity can be delivered to the grid, right? And so that's essentially how that technology works. It's been around since the 1930s, represents more than 95% of the deployed energy storage capacity worldwide. The nice aspect of this technology, looking here at this example here from Leadton, Michigan, so this is Lake Michigan right here, is that if you look at these types of systems for long duration energy storage, right? So this is multi-hour energy storage. This is 19 gigawatts of energy storage right here, or gigawatt hours of energy storage. And you get the power from this pumping station right here, which can provide 2.1 gigawatts of power. The nice thing about this is that you have a decoupling of power and energy. What I mean by that is if I wanted to store more energy, if I wanted to go to 19 to say to 38 or something like that gigawatt hours, what I would need to do is build out a bigger reservoir, right? Or build out a second reservoir. If I wanted to increase the power of this system so it could deliver more power, I would need to build out a pumping station, but you don't need to build both of them at the same time. And so that's a really nice feature because it allows for relatively flexible design. The second nice thing about pumped hydro is the fact that you're making use of natural resources. The fact that you have the water here from Lake Michigan, and you're essentially pumping water up and downhill, and water is a relatively cheap energy storage media. The challenge, of course, is that you're largely relying on the fact that there's natural infrastructure that enables you to make these sorts of this sort of energy storage device. If you didn't have Lake Michigan here, it would be pretty difficult to design a system like this. Another challenge is that these are not very energy dense. What I mean by energy dense is that you have to build them really big in order to store an appreciable amount of energy, right? And that means that you can run into problems associated with the environmental impacts of designing these types of systems, as well as not in my backyard type challenges. And so while we do have a lot of pumped hydro availability within the United States, you can be challenged in terms of how much more you can build out because these are such large projects that require a lot of capital cost, and it'll take a little while for you to get that payback. So what we become interested in is, well, maybe we can start to think about other ways where you could store electricity. Electrochemical batteries become very interesting for this application. Most of you are very familiar with batteries from the AA batteries, such as the Duracell alkaline battery I'm showing you right there. We tend to deal with batteries that are a little bit more sophisticated than this particular technology. But what I wanted to emphasize here is that we look at a wide range of battery technologies. And the reason we do that is because for many mobile applications, by mobile, it could be, the cell phone that I have right here or the laptop that you guys might be looking at this presentation on, right? Or maybe a battery that would go into a vehicle, either for starter lighter applications like a lead acid battery, or for as a traction battery, say like a lithium ion battery. The energy density of that battery is very important because that battery needs to be able to move around. So I want to store a lot of energy and I don't want it to weigh that much. For grid energy storage, we don't care that much about the energy density only because we don't need to move the battery around that much, right? And as a result, we're willing to give up a little bit of energy density if it gives us some benefits in terms of the price of the system and the lifetime of that system as well. And so we're willing to open up the design space going from enclosed batteries such as lithium ion or lead acid to systems that look a little bit more like chemical plants. So something like a flow battery, which I'll talk about today, or systems that try to combine some of the aspects of the enclosed battery and the flow battery. So something like a hybrid metal type battery right here, right? The key thing to take away for grid energy storage, though, is that price and lifetime are paramount. And so the format of the battery, you may not care that much about. What you care about is that it lasts for a long time and it's relatively cheap. But flow batteries provide us with some particular benefits in this application. So I wanted to talk a little bit about flow batteries here. And I'll say, as a chemical engineer, when I look at a flow battery, I feel that it falls squarely within the domain of chemical engineers or chemical scientists, and I can see the entirety of the chemical engineering curriculum within a flow battery. And hopefully I'll be able to give you some sense as to what I mean by that as I go through here. So the way a flow battery works is you start off with two separate tanks. One tank holds the negative species, one tank holds the positive species. You need a negative species and a positive species for a battery. Within that tank, you have the active species. So this is the species that actually stores charge. In this case, I'm showing you a vanadyl sulfate as an example. And that species is dissolved in an electrolyte, which is composed of a supporting electrolyte and a solvent. So this could be something like sulfuric acid and water, right? And these solutions are dissolved in these tanks. And how you're actually storing energy is that you're charging and discharging the battery by changing the oxidation state of these active species. And you're relying on the fact that these species are oxidized and reduced at two different potentials. And so there's a Gibbs free energy of reaction between these two species, which directly correlates to the amount of energy that you can store and release, right? And so you want these two species to be substantially different from one another in terms of the electrode reactions and where those electrode reactions exist on a potential scale. Where the electrochemical reactions occur is within a reactor, right? That which these two electrolytes flow through, and they're separated by a membrane. This reactor looks a lot like a fuel cell for those who are familiar. For those who are not familiar, it's a multi-layer configuration where in the middle you basically have a membrane separating two half reactions. And I'll go into that in a little bit of detail here. The purpose of this membrane, and it's typically something like a perfluorinated membrane, you could imagine something like Nafion that was developed by DuPont, is to allow ions to move back and forth between the two electrolytes to balance the electrons that are moving through the external circuit while preventing the active species from crossing over. So you want to have some sort of a perm selectivity so the active species stay on their respective sides of the battery, but the ions can move back and forth between the two electrolytes. Where the reactions take place are on porous electrodes that are directly abutted to the membrane. So if this is your membrane here, you have a porous electrode that's directly abutted to it, and the electrolyte is introduced to the porous electrode through a flow field right here. This is a blow up of a flow field that is typically used in advanced flow batteries. This is called an interdigitated flow field. The way you should think about this is that these lighter blue channels here represent open channels for the liquid to flow through. So they would be akin to these dark holes right here. And these sort of grayed out channels here basically represent a rib or some block between the two channels. And so what you'll notice is that these channels will dead end, sort of similar to my fingers overlapping over one another right here. And where these channels dead end, it forces the fluid through this porous electrode in with convective flux, right? And so you basically pump your fluid through the channel and then through this porous electrode. The porous electrode is typically something that looks like this. It's a carbon paper. You have sort of these larger pores here that are in order of 100 microns that allow for a relatively low pressure drop as you pump the liquid through. And then you have sort of smaller pores that you may be able to see here, which I'm showing with my cursor. And within these smaller pores, you have a diffusive flux to the catalytic surface where the electrochemical reaction will take place on these fibers, right? So these are the electron transfer reactions that I talked about at first. And the fluid basically will move through this porous electrode. It'll react, it'll come out the other end, and it'll cycle back to the tank. And so that's essentially the basics of how a flow battery works. So hopefully what you've seen there is I talked to you about a little bit about thermodynamics. I talked to you about transport, kinetics, separations, process design, and controls, how these systems operate, right? So it looks a lot, I think, like a liquid chemical plant for energy storage. The advantage of this particular structure, why you'd want to use this for grid energy storage, is that you're able to decouple power and energy scaling very similar to what you're able to do for pumped hydro. And the way you do that is the fact that these tanks here represent the energy storage capacity of the battery. And so if I want to store more energy for the battery, I can build out more tanks or I can make larger tanks, right? If I want more power, I basically need to build out more reactors. But you can imagine an installation where you can build out more energy and more power on an as-needed basis. It's relatively simple manufacturing for building these types of systems. You know, tanks and pipes are really easy to make, and then the reactor is basically sandwiching everything together. You don't really need clean rooms or anything like that that you might need for, say, something like precision machining lithium-ion batteries. These types of systems have high durability and relatively low maintenance costs in order to allow them to operate for long periods of time. And there's location independence as compared to something like pumped hydro. But as I mentioned, there's no free lunch. Redox flow batteries are suitable for long duration energy storage applications, what we could call energy intensive or energy rich type applications. And the reason is that they're not very energy dense as compared to the lithium ion batteries that we're all familiar with. An easy way to think about this is that when you have a lithium ion battery, you have thin films of electrodes that are sandwiched close together and only are, a little bit, only, say 40 microns apart from one another, right? As a result, it's a very dense packing. For this type of system, I'm having massive tanks where I have my active species diluted by an electrolyte. And then the entire structure is significantly larger because everything's separated out, right? And so what you give up in energy density, you hope to make up in lifetime, and you hope to make up in cost. And that's the game we're playing. And you can do so. So this is an example of comparing flow batteries. The capital cost of a flow battery is on the y-axis. On the x-axis is the discharge duration, which can be thought of as the energy of the battery divided by the power of the battery. You get a characteristic discharge duration from that relationship. And what you can see is that for flow batteries, when you go to shorter discharge durations, the cost of the battery is dominated by the power. So it's dominated by the cost of a reactor. But as they get to longer and longer durations, the reactor becomes a smaller and smaller part of the installation until you're asymptotically approaching the cost of the active materials that exist in the tank. So the way you should think about this is the reactor is getting smaller and the tanks are getting bigger to the point where you're largely paying for the tanks and not paying that much for the reactor, right? This is beneficial because if you think about a lithium-ion batteries, you have the same package. And so if I want to store more energy for a lithium-ion battery, I'm buying the same package over and over again, and I'm simply multiplying out that package. For a flow battery, though, if I want to store more energy, I can build out more tanks. If I want to have more power, I can build out more reactor. But the separation of power and energy allows you to have this change in battery costs as a function of discharge duration. The challenge that we'll see is that current flow battery technologies, even with this benefit in terms of the scaling of flow batteries, still are quite expensive as compared to lithium-ion batteries right now. And so VRB here stands for vanadium redox flow battery. I'll talk about that more on the next slide, but suffice to say that vanadium redox flow batteries right now are still relatively expensive on a capital cost basis, right? And even with future developments that we imagine in the vanadium flow batteries, so improvements in reactor design, decreases in vanadium cost, it still looks like they're going to be very close to what the cost of lithium-ion batteries are going to be, right? And so then it becomes a question of adoption. What we'd like to do is identify battery technologies for flow batteries that can allow us to get to significantly lower capital costs. And to get to those capital costs at relatively short discharge durations, let's say within the day time frame. And so that's what I'm going to be talking about from here on out with the time that we have left. To give you a sense of the vanadium flow battery, if you got excited after this talk and went out to buy a flow battery, odds are you're going to buy a vanadium flow battery. This is the state-of-the-art technology. It's available for multiple vendors within the United States and also around the world. And it's a very forgiving technology, which is why it's been a technology that's been so widely adopted for flow batteries. The technology relies on the fact that vanadium has 4 stable soluble oxidation states within a water window. Vanadium 2, 3, 4, and 5 of these different oxidation states. And the battery essentially relies on cycling between the vanadium 2 and 3 oxidation states on the low potential side for the negative electrolyte, and on the positive side of the battery, cycling between the vanadium 4 and 5 oxidation state. And this gives you an open circuit voltage of about 1.3 volts on that order, right? The nice thing about this technology is the fact that it's a single parent compound. And so for this ion selective membrane, if you're trying to shuttle protons across, if vanadium accidentally comes along for the ride, you will have an imbalance in your cell, but you can deal with that imbalance by simply shifting vanadium from one tank to the other tank during operation to rejuvenate the cell, right? So it has capability of allowing itself to operate for a very long period of time through these rebalancing activities. The second is that vanadium has a salvage value and will not decay over the lifetime of the battery. And so if you put vanadium in at the beginning of lifetime, you can salvage that vanadium at the end of the project period of the battery lifetime and get some resale value out of it. You might need to clean it up a little bit, but the vanadium is not going to decompose, right? We're not alchemists. And so this gives us some benefit for these types of systems where vanadium is a very attractive system to operate a flow battery. The challenge, as I showed you on the previous slide, is vanadium is quite expensive. For those of you who are familiar, no problem.
You guys picked the wrong nights. This is an actual somebody's presenting for MIT about how they do
Oh, sorry. I thought Thomas was talking to me. Apologies. I'll keep going. So The disadvantage of vanadium, which I sort of hinted at on the previous slide, is that vanadium is pretty expensive. The reason vanadium is expensive is because primarily it's used in steel manufacturing, right? To make high strength steel that will go into, say, very tall skyscrapers, things of that nature. And the challenge with that is that, because the vanadium flow battery market is so small, we are price takers for the steel market. And so if vanadium costs a certain amount of money for steel, or a certain amount of it is going into steel, that's the price of vanadium. And so if there's fluctuations within the steel market, these batteries can become more or less expensive. And so this is one of the challenges of this technology. And so people are looking to move beyond vanadium into other flow battery chemistries. And this is where I think there's a really interesting opportunity for not just academics, but also folks within industry. Because if you take a look at publications, which is a proxy for interest within the flow battery community or within flow batteries, what you'll notice is that there hasn't really been that much interest until actually quite recently, right? And so it's a technology that has been relatively understudied. And what you'll notice is that interest starts to jump up right around the time I was showing you that graph of solar getting cheaper and cheaper. So as people start to realize that solar technology or renewable technologies are really very interesting, we start to think about ways where we can store that electricity to make the renewable technologies more reliable. And that tends to correspond to this increase now in interest in the technology. The challenge, of course, as I showed earlier, is that the technology is still a little bit too expensive. In about 2014, these numbers are a little bit old, but I think the message is still there. Redox flow battery systems that you would buy, install costs were greater than $500 per kilowatt hour. And the DOE thought that it would need to be on the order of $150 per kilowatt hour in order for it to be broadly competitive in the energy storage market. And so when I look at this, I see that there's tremendous opportunities for transformational technology advancement through new redox chemistries that could be lower cost and new reactor designs that could improve performance, right? And so this is why I became interested in this area and why I think many people are very interested in this area. But once you start to look at how you might be able to improve vanadium flow battery technology or flow battery technology in general, we quickly find that there are many different pathways to success potentially. We could think about getting away from vanadium, going away from these transition metal salts that are dissolved in an acidic electrolyte to things like organics, potentially polymers or other cheaper inorganic materials, which I'll talk about in a little bit later in the presentation. Stepping away from aqueous acidic electrolyte, which can challenge materials compatibility, especially if you want to use any sort of metals or any plastics that you think can be eaten away by these acidic solutions, to maybe going to neutral pH solutions or even non-aqueous electrolytes to get to higher power and energy densities. Going away from ion exchange membranes, which are typically perfluorinated and which are expensive, going to maybe separators that are more size selective or rely on other methods of separating the two electrolytes. And then also going away from, we'll say, designs that are borrowed from adjacent technologies, such as fuel cells, to designs that, of the cells and systems that are specific to redox flow batteries. And so when we look at this, we could say that there are lots of different potential pathways to success, but because we're trying to optimize multiple different components, it's really unclear what success might look like. And the way to think about it would be, if you had the best active materials you could think about, right, would that necessarily get you all the way there? Or do you need a combination of active materials, electrolytes, and membranes to get you there? And so a lot of times when we try to think about this as engineers, we try to think about the balance between these different pathways to improvement and what opportunities we have to sort of design a system that can maximize all of these or balance these capabilities. And so to do this, a lot of what we try to do is do techno-economic modeling. Techno-economic modeling is really foundational for us to quantify and compare the performance and economic potential of a diverse set of established and conceptual grid batteries. And the way we try to look at this is to back translate from system level performance goals and price targets to materials and component level targets and properties. What I mean by that is I know what I want my materials, my system cost to be. I have an idea of what sort of performance I'd like to get. And what I'm asking myself is what combination of materials properties, cost parameters, and performance is going to get me there. And so what we're asking ourselves is, are there critical sets of interdependent materials properties that I should be aware of when I'm designing my flow battery? I want to know, how do materials design decisions impact other aspects of the system? So if I optimize an active material, does that all of a sudden pin me into using a particular type of membrane that's expensive, or a particular type of electrolyte that is really difficult to find? And then, are there technical roadblocks that might be obscured if I'm only thinking about this on the component level? Let me give you an example of that. I talked to you a little bit about potentially using polymers, right? The nice thing about maybe using polymers or macromolecules for redox flow batteries is that I can get away from systems that rely on charge selectivity, so things like perfluorinated membranes, to maybe using membranes that look a little bit more like a coffee filter or a filtration type membrane. But then you have to ask yourself, well, can I pump a polymer? Can I pump a macromolecule? And how much pumping losses am I going to incur in my system in order to operate? And what is that going to do in terms of my energy storage and my system performance? And so all of these kind of interdependent relationships is what we're trying to capture in these types of analyses. And so just to give you a sense as to how we go about this, when we're doing our cost modeling for flow batteries, we try to consider present day battery costs in order for us to level set our cost metrics and understand that we are actually matching up quite well with what's being offered right now by vendors. And this gives us a sense as to whether we're getting the right numbers and we're capturing the right general trends. And then what we do is try to project out to a future state where there's high volume production existing in a competitive marketplace. So you might think of this as a world where there are multiple gigafactories that build flow batteries. And what we try to do is look at similar mature products to learn what engineering will likely be utilized for the design and manufacture of these materials. We run performance cases from conservative to optimistic using a range of outputs to understand the cost drivers. We try to map out materials pathways then to reach low cost targets. And so what you should think about in the data that I'm going to show you is that what I'm trying to show you is like, what is, if things are working out to our favor, right? So this is an incorrect use of this, but maybe, if I was to say everything broke in my favor, what is the lower limit of cost, almost the thermodynamic limit of cost in terms of how low you can go for this technology? If you think you can get there in this future scenario, then it might be worth pursuing. If you can't get there in this future scenario and everything broke in your favor, then maybe you wouldn't be able to get there in the base case. And so the way we try to look at this is to look at battery price, which is in this case $100 per kilowatt hour, and I'm adding now a little bit of money now for some other balance of plant materials, which I can come back and talk about at the end of this. So this is without an inverter and without installation costs. I need to put in here the cost of the reactor. I need to put in here the cost of the electrolytes in the tanks. I need to have the balance of plant. So I mentioned tanks earlier, I should have mentioned it here. The balance of plant is basically the pumps, the tanks, the heat exchangers, all the parts of the batteries that you need in order for the system to operate, but don't actually store energy. And then because I want it to be a price and because I'm thinking about manufacturing, I need additional costs. So depreciation, labor, overhead, a profit margin, right? As an academic, I'm much more focused on the cost of the reactor and the cost of the electrolyte. The balance of plant costs and the additional costs we get from industry collaborators who we work with, as well as from the best practices on industry literature. So I'm going to primarily focus on the cost of the reactor and the electrolyte, but these other things I want you to know, we pay attention to what they might be, and they are important. In a little bit more detail here, the cost of the reactor is directly proportional to the cost of the materials that will go into the reactor. It's directly proportional to the resistance of the reactor as well. So a higher resistance reactor and a more expensive materials going to the reactor are actually bad for the cost. It's inversely proportional to the efficiency of the system, and it's inversely proportional to the square of potential. So that tells you the potential of the battery or the operating voltage is very important, and the efficiency of the battery is very important as well. You want a battery that operates at high efficiency. You want a battery that operates at high potential. For the cost of the electrolyte, we can see the cost of the electrolyte is essentially a summation of the active materials cost on the positive and the negative side, the cost of the salt that goes into the electrolyte, and the cost of the solvent that goes into the electrolyte. So this could be something like water and sulfuric acid. If you're using something like water and sulfuric acid, these two terms here tend to be really small as compared to the active materials costs. But if you use something like a non-aqueous electrolyte, these terms right here are actually become appreciably large and you need to consider them. And then, of course, the cost of the electrolyte is inversely proportional to the potential of the battery and inversely proportional to the efficiency of the battery as well, right? And so taking these sort of design equations, what I'm able to do is to develop cost utilization maps or design maps rather. And so what I'm going to show you here is a plot, one example that we could plot out, but I think this is a useful one to think about, where I have cell voltage on the y-axis. Remember, cell voltage impacts the cost of the reactor and also the cost of the electrolyte. And I have area-specific resistance, which is directly proportional to the cost of the reactor on the x-axis. And what I'll show you here is contours of isomolality. So that's moles per kilogram. And within here, what you're looking at is a region in which a non-aqueous redox flow battery would be able to hit the design metric of $100 per kilowatt hour. And this is, of course, without the inverter and without the installation costs, right? And within this, you can sort of tell a little bit about what are the cost drivers. So for example, if I have a battery that has a relatively high resistance, because of this, the high resistance means I'm going to have a costly reactor, which means that I need to be able to operate the battery at a relatively high voltage, and I'm going to need high concentrations of the active materials. However, as the reactor gets less and less resistive and therefore cheaper and cheaper, I actually open up my design space to while I can have a battery that operates at maybe slightly lower voltages and has slightly lower active species concentrations associated with it. I can make a similar design map for aqueous batteries as well. And in this design map for aqueous batteries, we can see that we have, again, sensitivities associated with the resistance of the battery. The less resistive the battery is, the cheaper you can get. And also the wider the design space you're able to have in terms of the active species concentrations and also the operating cell voltage. These kind of maps can then be converted into key design metrics. And this is, say, for example, for something like 5-hour discharge. So this might be shifting energy from the middle of the day to the evening, say for solar energy or something like that. And what you get out of it is some guidance in terms of active materials costs, in terms of molecular weight of those active materials per mole electron. And you get some guidance for aqueous flow batteries in terms of the cell voltage, or in terms of the ASR of that battery, the area specific resistance that is. And for non-aqueous batteries, you get a similar set of metrics in terms of active species concentrations and molality, cell voltage, ASR, and also the salt cost factor, which has to do with the amount of salt that exists within the electrolyte. And all of this gives us some sense as to what is the design space, but also what are the technology risks. And so for something like a non-aqueous flow battery, there's a much wider design space that's available, but there's also a lot more challenges associated with the materials targets that you would need to hit, and the fact that we don't actually have commercialized non-aqueous flow batteries right now. So this might be something for further off in the future. But for aqueous flow batteries, we already have the vanadium battery, which I talked about. And essentially what we're trying to do is identify aqueous flow battery chemistries that might be a little bit cheaper than vanadium. And so there might be less technology risk here, although there's a slightly smaller design space. So what you might end up by seeing is that the next generation of flow batteries might be new aqueous chemistries followed by non-aqueous flow battery chemistries afterwards. And so I wanted to finish up here quickly and not go too far over time, because I really do want to have a little bit of discussion, and I want to be respectful for people's time this evening to sort of say, okay, where do you go now that you have these design maps? What approaches are we taking? And so one particular approach we're looking at is low-cost commodity scale inorganic materials. Don Sadoway, who I believe gave a talk here, Professor Don Sadoway, a number of years ago, likes to say, if you want to make a dirt cheap technology, make it out of dirt, and preferably make it out of local dirt, right? I really like that statement. And this is actually an example of a way to get to low cost technologies using dirt. In this case, the dirt I'm using an example of is sulfur. If you're going to pull oil and gas out of the ground, sulfur is usually going to come along for the ride, even in a world which uses carbon sequestration. And so this sulfur is already manufactured for us right here. It's sitting in these pyramids, and this is in Alberta, Canada. The Alberta tar sands have a lot of sulfur associated with it. Could we use this sulfur to store electricity? It's among the cheapest ways to store electricity right now in terms of dollars per kilo amp hour of charge storage. And so we've been exploring different methods of using sulfur, either paired with oxygen. This is work we did with Professor Yet-Ming Chang in the Material Science Department at MIT, and which ultimately led to the formation of Form Energy, who's now looking at slightly different technologies, but this was one of the technologies that started this very successful spin out. And I was happy to be a participant in that work. The work was led by Yet. Another technology that you might think about, and this is work we're doing with RPE, is using these polysulfides in combination with a permanganate type solution, which is a very cheap inorganic material. And we're actually working on this with a Raytheon Technology Research Center and a couple of other collaborators looking at the potential of using these types of batteries as well. So there are ways to get to low cost, we believe, through commodity scale inorganic materials. Another way you could get there is through engineered molecules via molecular functionalization using tricks in organic chemistry. And that is to take organic molecules and begin to modify those molecules to impart particular properties that you would like on those molecules. And if many of those organics are coming from petrochemical streams, you can get them at relatively high amounts from the petrochemical industry, and you can modify them to be used for energy storage. And so depending upon the way you modify particular families of molecules, you can get relatively low equivalent weights. You can get molecules that would have low crossover, molecules that can enable multi-electron transfer, and molecules that can be even liquid at room temperature. And you can imagine, using that molecule as a solvent, not just as the active material. As a chemical engineer, I'm an okay chemist. And what this means is that I'm always looking to engage with a strong collaborator network within the chemical sciences, working with smart organic chemists from different universities and from the national labs to identify new molecular families that we can potentially use for energy storage applications. And what I want to do is, for the remaining time, give you an example of some of the work that we're doing in that area before I wrap up here. And so, whoops, I'm going the wrong way here. And so where we started looking at organic molecules that might be available to us is to say, well, how are organic molecules used in lithium-ion batteries? And that starting point is overcharge protection in lithium-ion batteries. The way you might think about this is, if I have a battery pack, which is in this case 4 cells in series on a string together, what you're able to measure is the voltage of all 4 of those batteries. But what you don't know is what is the voltage necessarily in each one of these batteries, and what is the capacity access of those batteries. And so if you have, for example, 3 batteries that are designed a certain way, and the 4th battery has a manufacturing defect, as you get to high states of charge when you're charging up your battery, you have a tendency potentially to overcharge one of the batteries in the string. This can lead to thermal runaway within this battery, and therefore a thermal event that could threaten the entire battery pack. And so one way you can think about addressing that is using something called overcharge protection, which is you have a component within your electrolyte that will activate when the battery starts to overcharge and move to arrest that overcharge activity. And in this case, this one will work by shuttling electrons through the cell itself, arresting the potential. And so how this actually works is that you have this lithium-ion battery, it's charging. You get to the top of your state of charge. Now you start to go into overcharge, you're breaking down electrolyte, the cell's going into thermal runaway, the potential starts to jump up fairly dramatically. The shuttle kicks in when the potential goes above a certain point, and it begins to redox cycle from one side of the cell to the other, creating an ionic short circuit. This potential is therefore held. The battery does not go into thermal runaway until you start to discharge the battery again. The shuttle switches off, the battery is saved and starts to discharge. And you can run this multiple times if you say you have a weaker cell in a particular string. This idea has been around since the 1980s. Early on, people were using halide type systems, then going to metallocenes, and ultimately then going to aromatic molecules. These changes corresponded to the cathodes, or the positive electrodes of batteries, going to higher and higher cell potentials, which meant that you needed higher and higher voltage protection materials. The reason these are interesting to us is because for these organic molecules, you can begin to tune some of the electrochemical properties. And by tuning those properties, you can impart significant improvements in performance. Just to give you an example here, this is a battery that uses lithium iron phosphate on the positive side, graphite on the negative side. And I have two redox shuttles that we've put in as an example. The first one here is this N-ethylphenothiazine, right? And what you can see is that this redox shuttle will operate at 3.4 volts and operate stably for about 1,750 hours of overcharge protection, right? But if I put on now these perfluoroalkyl groups onto this molecule, I can increase the working potential up to 3.8 volts, which gives me a little bit more access capacity on my battery, and it'll run for over 6,000 hours before it starts to break down. And so it's these little tweaks in organic chemistry that we're going after to try to dramatically improve performance. The challenges that we face are when we go from overcharge protection isn't a battery additive. I want to go from a battery additive to an active material in the battery, which means that the concentration requirements of this active material need to increase tenfold in both states of charge, but not only its reduced state, but its oxidized state, right? I want to get molar concentrations, not millimolar type concentrations, right? In order to do this, when I'm identifying new materials, my screening needs get significantly higher if I want to run them in these battery cells here. I'm going from milligrams of material to grams of material per experiment. And I can tell you something, if you want to lose friends in organic chemistry, tell them that you want grams of materials per experiment, and then tell them that the material didn't work and you need to get them to make more grams of those materials. You get to make that request once, and afterwards, they don't really want to work with you so much anymore. And then you have to think about stability here. For these for these additive materials, for the active material to oxidize and work its way back across the cell, it's usually doing this in seconds to minutes when it's in its oxidized form. However, for a redox flow battery, you want it to be in an oxidized form for hours to maybe even years, right? And you need it not to decay, right? And so how are we going to actually get around that? We need to have very stable active materials. And then, of course, there are other design considerations, including things like membrane compatibility, other components in the cell, all of which drive us to new design strategies. And so just to sort of give you an example, using something like this N-ethylphenothiazine, which was a redox shuttle first developed by Jeff Don, and working with Susan Odom at the University of Kentucky, we've started to explore different ways of modifying this molecule to, say, improve solubility within electrolytes to get more storage capacity for our battery. We've looked at tailoring our redox potentials to increase the cell voltage to allow the battery to operate at high voltages and store more energy by adding electron donating or withdrawing groups. And then we've also looked at increasing molecular capacity by modifying these materials to stabilize 2-electron transfer through an extended electronic structure, right? All of these are tweaks of organic chemistry. And the important part here is our design ethos focuses on 2 to 3 step syntheses and scalable routes. The idea being that if I identify a particularly promising molecular structure, I want it to be readily scalable, and I want it to be a relatively simple transformation so that hopefully we can scale these up without blowing the cost out of the water for the battery. I talked a little bit about making and losing friends in organic chemistry. One of the ways we try to avoid that is by being very careful about the battery prototypes that we're building. So this is an example of a subscale cell. This is around the largest cell that we build in the laboratory. This usually has an active area where the electrochemical reactions take place of about 25 square centimeters. And this is usually the smallest unit that industry will consider before thinking about scaling to a full stack. Because we're an academic laboratory and because we're doing exploratory research, though, this subscale cell is perhaps a little bit large, especially for some of the initial work that we're doing. And so a lot of work that we do is in a research scale cell that's about 2.5 square centimeter active area. So it's about 10x smaller than the subscale cell right here. The reason we do this is because we're trying to better control our reaction environment, reduce our materials need, and improve the safety of the electrochemical process. It allows us to test more things more safely and also with a better control of our reaction environment. But of course, as we design these types of systems, we design them so that they're scaled models of this subscale cell, and we make sure that whatever data that we're getting in these small cells can be scaled to the large cell. So when anything pops or gets really exciting for us, we can take it to this larger cell, prove it out, and then maybe we can interface with industry in that handshake to see if we can scale that out into sort of full system designs. I'm getting towards the top of my time here. So what I want to do is maybe go through avoid the next couple of slides. What I was going to talk about a little bit is leveraging flow cells as analytical platforms. So different configurations that you can use to test battery materials. I'm going to avoid that for now. But what I wanted to give you an example of is just a way that we've been able to take some really interesting organic molecules that have been developed by the Odom group. Oops, I'm going the wrong way, apologies. And test them out electrochemically using benchtop methods and then cell cycling methods to identify new materials. And so this is how these types of approaches help us more quickly identify new materials that can allow us to meet targets. And these cell designs also give us an opportunity to test a variety of other things with the reactors, including developing models to determine performance, designing new low resistance cells, and identifying different component properties. But where I wanted to end or finish up, and hopefully this will drive conversation, is to say, where are we going from here, right? So what are things that we're trying to do better in order for us to get to better flow batteries more quickly? One of the areas that we're really trying to work on is trying to understand how computation can help us to design better materials more quickly. We're trying to sort of see, well, maybe we can guide synthesis of matter with precise properties through the use of computational tools such as quantitative structure property relationships and genomic calculations associated with different molecules. And can we bring these things together to identify, what are the target set of properties that we would need to develop new molecules, new materials, and new interfaces for the batteries? The challenge that we're facing in these areas is while these models can be developed, I'm showing you examples of such models here, the outcomes of these models are not necessarily universally applicable. They can be often dependent upon local factors like the molecular species that you choose, the electrolyte composition, the experimental setup. And because of this, this means that some of these, if they're not universal, we might need to go through this process multiple times. And so an area that we're trying to identify is what are generalizable rules for designing materials that can give us low cost and high performance for these batteries. Another area that we're very interested in and is a grand challenge is coordinated designs of molecules and membranes. I sort of gave you an example of the polymer beforehand. And the challenge that we're facing is that if we go to small molecules, like this is a redox active molecule, you can also think of it as a monomeric unit. These are typically paired with expensive ion exchange membranes. However, if you can start to daisy chain these molecules together in oligomers, polymers, or even something as large as a colloid, this opens up the membrane design space to go from something which is charge selective to things that are more size selective, like nanofiltration membranes, polymers with intrinsic microporosity, or also materials such as separators that look a little bit more like a coffee filter. But the balance you're trying to strike here is what is the sweet spot across this, this design space here. And you're trying to balance the transport of those materials, the redox kinetics of those materials, their solubility or suspendability within the electrolytes, as well as the cost of these types of materials, all of which need to be balanced to enable a more advanced redox flow battery design. Personally, I think that the sweet spot is around oligomers. Anything that gets a little bit bigger than that, it's very difficult to pump these types of systems, and the cost of synthesis can go up quite a bit. But the oligomer may allow you to access really low-cost nanofiltration membranes that are widely available in industry right now. And then finally, there's the question of, if I want a battery to operate for 20 years, how do I know it's going to work for 20 years? And how do I know that before I operate it for 20 years? And so a lot of what we're trying to do is identify and mitigate decay mechanisms that exist within these new battery chemistries, right? And so we're trying to figure out what are modes of performance degradation and how are we able to predict it before the battery operates for its full lifetime. And this involves things like computational analysis, very careful spectroscopic type characterization of active materials at early stages in battery operation to see if there's any minor decay mechanisms. And then, of course, a lot of testing that has to be done early on to identify what mechanisms may exist. To be clear, a battery can decay, and that might be fine as long as you have methods of mitigating that decay, right? So you might have a really cheap molecule that decays, but you could basically fish that molecule out of the tank and put in a fresh molecule every now and again. So think of it like changing the oil on your car. That might work out as well. Or you might have materials that can be regenerated on site during battery operation. And so the material might decay for a while, but you're able to regenerate it on site and use the battery. So almost like the battery gets a tune-up every 5 to 6 years and you're able to operate again. These are all sort of potential operating modalities for these types of systems that we're exploring. And so I think I'm over my time here, but what I wanted to leave you with was a couple of quick conclusions. The first is that I think early stage techno-economic modeling can really help to inform research directions and highlight technology bottlenecks and really help us to identify what are maybe the best pathways going forward and what are the key problems that we need to address at an early stage to get to a low cost technology. Ultimately, redox flow batteries show a lot of promise for long duration energy storage, provided we can get to inexpensive electrolyte chemicals and provided we can get to reactor designs that are relatively cheap and high performance as well. And that's what we're going after. And the way we think we can go after that is by using redox probes and diagnostic platforms to illuminate new pathways to cost-effective battery materials. This was some of the stuff I didn't get to cover in as much detail, but the idea is basically, finding a way to engineer to better batteries rather than trying a lot of different molecules and hoping that some of them are going to work. These are pathways that we can design and go after key targets. And so with that, I thank you for your attention and the opportunity to speak with you. And I want to briefly acknowledge my research group who did most of the work, as well as collaborators in industry, Rob Darling and Mike Perry from United Technologies Research Center, now Raytheon Technologies Research Center, Kevin Gallagher at Argonne National Laboratory, and Kyle Smith at the University of Illinois. And thank you all for your attention. And hopefully people are able to stay on for a little bit of Q&A. But if you can't, certainly please feel free to reach out to me via email, and I'm happy to have a chat with you. Thank you again for the opportunity, Paul and Juan, and I'm happy to take questions as they come.
Thank you. Thank you, Dr. Brushett. We have
Yes, thank you very much.
We have two in the chat section. I don't know if you can see them.
Yeah, let me kill my share. That way I'm able to see you guys. There we go. Excellent. And I'm happy to pull up the slides again, but it's a lot easier for me to talk to a face than to talk to my slides.
So where is the chat, Juan?
Yeah, so I'll do the first one. What are the current and eventual potential? Oh my God, I don't know what the symbolism is there. Out efficiency. Can you see that?
I can. If is Tom Barr here and can maybe speak to it, I'm happy to answer it, but I also want to make sure that I'm getting at his or her question correctly.
Yes, you got AC power on the grid coming in. You have 100 kilowatt hours. You charge the battery. When you discharge, how many kilowatt hours go out on the grid AC?
Yeah, so that's a really good question. And a lot of that will depend a little bit on, which I didn't talk as much about, your connectivity to the grid, right? But generally, these types of batteries, you want to operate at about 80% or more round trip efficiency. That's energy efficiency. So if you put in, 100 kilowatt hours, you want at least 80 kilowatt hours to come back out, right? The way you're able to control that is through the Coulombic efficiency of the battery, which tells you your electron efficiency, electrons going in and electrons coming out. And then your voltaic efficiency, which is essentially the voltage at which those electrons go in and the voltage at which those electrons come out. And then of course you have other inefficiencies along in the process that you need to balance.
And where are the vanadium flow batteries now on this?
So that's a tricky question because people don't usually report that until you want to buy the battery. But I would say, and you can kind of fudge those numbers a little bit depending upon what's the current that you're operating at. And so if you look at academic literature, oftentimes that might not necessarily be the best representation. But I would say it's usually the numbers that I've seen are anywhere between 60 and 75% efficiency. But some of that, I think the more advanced systems are around, say, 70 to 75% efficiency right now. Does that make sense?
Yes. The other thing I wondered about, you spoke about grid application, and that's great.
Yeah.
Obviously, we all hope it gets there. Is there a market entry, a high value application somewhere short of the grid that would get manufacturing started and industrial use started and get the whole collective creative juices of that flowing?
Yeah, absolutely. So that's a great question. And sort of one of the reasons I didn't go into this as much detail is that the flow batteries are expensive, is because we don't make a lot of them, right? So if you don't make a lot of them, everyone is sort of a boutique build. And so you don't get the benefit of economies of scale like you do with lithium-ion batteries right now. And so a lot of it is finding, as you say, applications that have a lot of bang for your buck, and where they're not necessarily very good alternatives, right? That way, you can put in a system that might not be the best you could possibly do, but it gives you a chance to prove out the technology. A lot of where people think that you can go with flow batteries right now are sort of what I would call behind the meter type applications. So sort of applications where you have somebody who cannot afford to have a particular system go down, right? So it could be like you said, manufacturing, where if you have a blackout and you have a lot of automation, you don't want that to go down.
Right.
Or something like a school or a hospital or things like that. You want to get away from a diesel generator. This is typically where you're starting to see these batteries go in. The hope is that you can kind of ride the cost curve down by scaling in those areas, and then you get out to the broader grid and you can be much more competitive.
Okay, thank you.
No problem.
Do we have any other questions?
One more question if we have time for it.
Go ahead, Chris.
Sure, go ahead.
Thanks for your excellent talk, Dr. Brushett. It was really cool to see all the different areas that you were speaking of. I'm kind of curious about, for me, it seemed you talked about a lot of technologies, but I'm particularly interested in kind of the aqueous and especially like neutral pHs and organic molecules, as they seem to be kind of the very cheap and relatively stable. And I'm kind of curious, like in these organic molecules, is there some intrinsic trade-off between redox potential and solubility and stability that kind of makes it hard to optimize all three at the same time? Is there a reason why it's kind of hard to find that holy grail of molecule?
Yeah, that's a great question, Chris. And sort of the connectivity isn't necessarily a one-to-one-to-one, but there's certain trends that are relatively sort of well established at this point in time. So for those who maybe have a little bit less background, Chris is speaking as a little bit of an expert here, I think. You want to go to neutral pH because a lot of organic molecules tend to destabilize under deeply acidic or deeply alkaline or acidic type environments, right? And so finding organic molecules that are stable in those environments are a little bit challenging, right? The other reason you want to go to neutral pH is because the breakdown of water into hydrogen and oxygen is a lot easier under acidic environments and alkaline environments, but a lot harder under neutral environments, right? And so that gives you a wider window of kinetic stability for your water, even beyond the thermodynamic window. So you have active materials that are going to be a little bit more stable in that environment, and you have a wider window with which to operate in. The challenge that you typically end up by facing with organic molecules, even in that environment, is your oxidative stability on the positive side of the battery. At some point in time, as you get to higher and higher oxidative stability, it becomes pretty easy to rip apart carbon-carbon type bonds on the electrodes, as opposed to just abstracting an electron and charging the species, right? And so while you'll see there's a lot of organic molecules that people are very interested in under aqueous environments that people look at under the negative side, so the lower potentials. On the high potential side, it's actually very hard to find things that are stable enough. So even if you have that wide open space, it's hard to find someone who can live in that environment. Does that make sense?
No, yeah, definitely makes sense. And then I was just one other kind of curiosity question. Is there any of the kind of particular areas or particular chemistry that you're excited about these days, and kind of like, oh, that's a direction I think is would be really interesting?
Yeah, so that's a great question. So I've done a lot of work under non-aqueous conditions, and I think it's really interesting from a scientific perspective, but certainly in terms of a technology readiness level, it's not going to be there for, I think, at least 10 years or something like that, right? I'm actually very interested in the use of unusual solvents in these batteries. And I think one of the areas that's really interesting, you mentioned sort of the use of neutral pH type electrolytes. I'm also interested in acidic electrolytes that have relatively high stability windows. So you can think about batteries that often operate with methyl sulfonic acid, right? People have been shown that you can operate those types of systems under relatively concentrated conditions north of about, say 1.7 volts, right? Where the stability window of water thermodynamically should be 1.2 volts. So I think that's a really interesting area to sort of identify high voltage aqueous batteries that rely on kinetic stabilization. Just for those on the phone, a nice example of that is a lead acid battery. A lead acid battery operates at what, like about 2 volts or something like that, but it operates in water, and you're basically relying on the fact that water breaks down very, very slowly on lead electrodes, right? And so you can have this incredibly high voltage for the battery, even though thermodynamically you should be very unstable. Kinetically, it's not that unstable at all. And so I think that taking some of those examples and using them in flow batteries would be really interesting. And so that's kind of what I'm pretty excited about.
Awesome. And thanks again, Al, for the awesome talk.
No problem. My pleasure. I guess there's one more question, Ohiwa, if I'm happy to answer it, but I also want to be respectful of people's time, during a weekday. Okay. Yeah, I got one more here in the chat. It's by Ohiwa. I apologize if I'm butchering that. It says, in chemical engineering, what is the most interesting thing you've done so far? Most fun, most challenging, and how did you get your PhD in only 1 year after getting your master's? So I'll start with that last one. That has to do with a quirk in the University of Illinois, where you can write a master's thesis on your way to the PhD, but you can do it whenever you want. So I wrote a master's thesis, and then my PhD accelerated, and I was able to get a PhD the next year. So it's sort of, a lot of people will go and get the PhD and not get the master's. I thought I would get the master's along the way, and so that's how that worked out. But so that's why it's a little bit odd. In terms of chemical engineering, what's the most interesting thing I've done so far? I think the thing which I like the most is working with students. I had known that I wanted to be a faculty member, but I hadn't really appreciated, the joy of watching students go from, coming into the laboratory and just beginning to learn, to then developing into smart, independent researchers who come up with ideas that I could have never thought about, right? The fun thing about starting a project is I have a general idea of where we want to go, but I have no idea how it's going to end. And usually when it ends, it's way more interesting than anything I could have thought about a priori, or I could have thought about it by myself. So that's been, maybe the most fun that I've had, as a chemical engineer. And I think the most challenging is really the research, right? The fact that, I want to have an impact as an academic, and I'm trying to find a way to contribute to the transition to a more sustainable future, but then looking at just how quickly things are going in terms of climate change, how technologies need to be ramped up really, really quickly, and trying to make sure that I'm positioning myself and my research group to hopefully add value and contribute in that area. And that's just been very challenging, but also very rewarding, because there's a lot of different problems. They're all very complicated, and they're all quite difficult, right? And so that's, I think maybe the most challenging part of what I'm doing right now. But I certainly enjoyed it. I'd like to think I'm up for the challenge, and like to think, many at MIT are up for it as well.
Okay, last call.
Very good. Yeah.
Questions? If not, Dr. Brushett, thank you so much for joining us on behalf of the MIT Club of Rhode Island and those who attended. Thank you so much. This is being recorded. I'm going to stop recording now.